Industrial steam turbines generate immense rotational power, but raw power is ineffective without a system for precise regulation. In a power generation setting, the mechanical load placed on an engine is rarely constant. As factory machines engage or disengage, these continuous fluctuations threaten the stability of the entire system. This graph illustrates the core engineering problem. Without intervention, there is a direct inverse relationship between load torque and engine speed. When the load on an unregulated engine increases, its speed falls. To function properly, an engine must maintain a specific mean speed, the target operational speed required over multiple cycles, despite these external disruptions. Maintaining that mean speed requires the automatic regulation of the working fluid, the steam or fuel entering the system. As the load increases, the supply of fluid must increase accordingly. At industrial scales, a human operator cannot monitor and adjust a throttle valve with the necessary speed or precision. The system requires a dedicated mechanical component to manage the intake. Early industrial machinery relied on the integration of a mechanism capable of sensing a speed deviation and physically correcting fuel intake in real time. Analyzing mechanical speed regulation requires distinguishing between the functions of a flywheel and a governor. A flywheel operates strictly inside the engine to manage the turning moment. It smooths out the power fluctuations generated during a single combustion cycle. Physically, the flywheel is a reservoir of kinetic energy, passively absorbing power during the power stroke and releasing it during the dead strokes. A governor manages a different operational domain, external load variations that occur across multiple engine cycles. Unlike the flywheel, the governor does not store kinetic energy. It acts as a dynamic mediator, monitoring rotational speed and physically adjusting the engine's fuel supply valve. While the flywheel masks the intensity of a single engine stroke, the governor serves as a closed-loop mechanical feedback controller to ensure long-term stability. Centrifugal governors are categorized by their loading mechanism. Tracing from the deadweight loaded type leads to a foundational design, the Porter governor. The internal kinetic chain of this mechanism translates rotation into linear displacement. At the center is the vertical spindle. Driven by the engine through bevel gears, the spindle's rotational speed is a direct proxy for the engine speed. Attached to the spindle are the flyballs. As the spindle turns, these masses revolve and are subjected to an outward centrifugal force. The lower arms connect to a central sleeve. Keyed to the spindle, the sleeve revolves while sliding vertically between mechanical stops labeled S. The sleeve is linked to a bell crank lever, which translates vertical sliding into the rotational movement of a throttle valve inside the fluid supply pipe. This specific anatomy creates a continuous mechanical link between the rotational speed of the engine and the volume of fluid allowed to power it. Under steady-state conditions, the outward centrifugal force on the flyballs is inward radial force. This inward controlling force is provided by gravity acting on the mass of the sleeve and the balls, pulling the mechanism downward and inward. If a sudden increase in external load is applied to the engine, the equilibrium shifts. The engine speed drops, instantly reducing the rotational speed of the governor spindle. This reduction in speed weakens the outward centrifugal force acting on the flyballs. The inward controlling force becomes dominant, pulling the balls toward the spindle and forcing the central sleeve to slide downward. This downward motion pulls the bell crank lever, pivoting the throttle valve to a wider angle and increasing the flow of working fluid. The increased fluid generates the necessary power to overcome the new load, recovering the engine's mean speed. The system has completed a mechanical feedback loop, sensing a deficit, actuating a correction, and establishing a new dynamic equilibrium without electronic intervention. Theoretical engineering defines an isochronous governor as a mechanism with infinite sensitivity. Mathematically, isochronism exists when the range of speed is zero across all radii of rotation within the working range. In an isochronous system, the governor would maintain an identical rotational speed, regardless of the load applied. However, this state is physically impossible for the Porter governor. For speed to remain identical while the radius changes, the vertical height from the pivot to the ball's center must remain constant. The rigid geometry of the Porter governor dictates that any change in radius strictly forces a change in height. Gravity-loaded governors must therefore accept a slight variance in mean speed to function. If a perfectly isochronous governor could be engineered using specialized springs, it would introduce new operational risks. In practice, an isochronous governor lacks the stability required for real-world engine control. Because the mechanism is perfectly sensitive, it cannot settle at intermediate positions. Any fraction of a deviation from the target speed causes the mechanism to overreact, a phenomenon known as hunting. Hunting causes the throttle valve to slam between fully open and fully closed, starving and then flooding the engine, creating violent power fluctuations. To prevent this oscillation, designers intentionally engineered a degree of insensitivity into these mechanisms to ensure operational stability. Engineering requires the management of physical trade-offs, sacrificing absolute sensitivity to achieve the stable, enduring control that built the industrial world.